Okay, so today we will discuss about millimeter wave passive components like filters, resonators, their basic properties, and couplers, power dividers, and finally different types of transitions. So passive components like bandpass filter or coupler, it is very popular in any wireless communication systems. For example, if we design any transceiver system, so in transceiver system, then the first component will be the antenna, and then we have to use a bandpass filter. So bandpass filter, it not only eliminate noise, it will also eliminate undesired bands. So after bandpass filter, if we use a single antenna for both transmission and reception, so in that case we have to use one isolator or some SPDT switch or maybe some ortho mode transducer. So after that we can use different types of receiver architectures. If we use homodyne architecture, it does not involve many passive components, but if we use super heterodyne receiver technology, it involves many passive components, particularly bandpass filter. So here I am going to show you one more receiver architecture. It's known as mixerless receiver architecture or 6-port architecture, which use many passive components. So this is the schematic circuit of the 6-port receiver. So here you can see the RF incoming signal. It is fed to one branch line coupler, BLC. So this is one type of coupler which will divide the power into two ports when with a phase difference of 90 degree. So this architecture, it's using 3 branch line couplers. So not only that, one power divider, usually Wilkinson power divider, and local oscillator signal, it is fed to this power divider. So all of these are passive components. Right side you can see the microstrip line footprint or layout. So this is the PCB part, PCB layout of the 6-port receiver, and the only RF active device is used detector, basically detector diode at millimeter wave frequencies. They are connected to this first branch line couplers output port, port 3, port 4, and bottom one, port 5 and port 6. So we need basically 4 RF detectors, and with this we can demodulate any signal and it works as a receiver. So you can see so many different types of passive components are being used in this particular receiver architecture. So the size of this receiver architecture in terms of lambda, it's quite big. That's why it's not popular at lower microwave frequencies, but it's very popular at millimeter wave frequencies, because the accuracy of this receiver is much higher compared to super heterodyne or homodyne receiver technology. I will give you one more example. So this is a typical antenna array with accessories used for synthetic aperture radar system. So this orange color patches you can see, they form one array antennas. It is being used for both transmission and reception. So it is followed by TR module. So inside TR module we have isolator, one passive components, and also bandpass filter, that is again passive components, and just before it we have a pin diode based 4-bit phase shifter. So this is for scanning purpose, and you can see there are many Wilkinson power divider. So this is a 2-way 1:1 Wilkinson power divider, this is one more. So there are so many passive components involved in any radar architecture or any actual wireless systems. So before going to the coupler and filters, let us discuss about a basic resonator, which is dielectric resonator. At millimeter wave frequencies, metal loss is very high. So we usually try to avoid any metallic structure at millimeter wave frequencies, and if we can make some resonator based on dielectric waveguide, in that case we can avoid metal loss to some extent, and the only loss we will be facing is dielectric loss. So, that is how we can minimize loss from any structure. And resonators, where are they used? They used in filter design as well as they used in antenna design. So, when we will be using in antenna design, then in that case we expect radiation from the resonator, or the quality factor due to radiation QR should be smaller. And when we use similar resonator in filter design, so what we expect that all of the electromagnetic energy, it should be confined inside the resonator, or quality factor should be as high as possible. There are different shapes of dielectric resonator, like cylindrical resonator, rectangular resonator, hemispherical resonator. So, most popular design is cylindrical resonator, and let me discuss quickly some basic properties of a cylindrical dielectric resonator. Usually different types of dielectric materials are used to make this dielectric resonator. So, epsilon r is high, usually typically it is more than 10, and the only thing we have to keep in mind that the loss tangent value or dielectric loss should be as small as possible, because we are using dielectric resonator to minimize losses. So, let us start with the cylindrical dielectric resonator. As you can see in this figure, we have a cylindrical dielectric resonator. Let us consider it is isolated from rest of in space, and z axis, it represents the axis of the cylinder, and typical materials we used with epsilon r 10 to 100. So, it is of compact size, but only problem we face is that it is sensitive to temperature variation and mechanical vibration. So, that is why it is not very popular in space applications, where we may have to deal with large temperature variation. Now, since we have dielectric air boundary, so we will be having hybrid modes. So, typically it supports hybrid mode HEM suffix NML. NML is the mode number, and if you recall image guide, so almost similar analysis we can follow here. And HEM NML, in addition to this we have TE or TM to Z. So, almost transverse electric or transverse magnetic with respect to Z axis. It also supports hybrid modes HE when EZ dominates over HZ, and EH when HZ dominates over EZ. Now, how we fix the mode designation? So, N, it represents number of extrema, maxima or minima along circumference, so phi direction. M, it denotes the number of extrema in along radius, and L, it denotes along axis. So, if n equal to 0, that means there is no extrema along phi or no variation along phi. So, we will call this mode as axisymmetric modes. For example, TM 0 ml mode or TE 0 ml mode. These modes are axisymmetric mode, and in some cases we will see L or along Z we will be facing less than half wavelength, but there would be one maxima or minima. So, that is why sometimes L is replaced by delta to represent that its length is less than lambda g by 2, and we call it then TE 01 delta mode for the fundamental mode. So, for TE 01 delta mode, then it is axisymmetric mode. We do not have any variation along phi, we have only one extrema along radius, and along Z the dimension is less than lambda g by 2. So, some characteristics of this TE 01 delta modes, it is written here. So, we do not have any del phi variation and less than a half cycle variation along Z, and not only that, on the dielectric air interface electric field is parallel. So, that means we can replace this dielectric air boundary by one magnetic L. magnetic wall. So, the non-zero field components, mainly we have E phi components and both the radial components and z direction component of magnetic field vector H. So, let me show you the field plots. So, remember the axis, it is in z direction, then right hand top right figure, it shows the electric field variation. It clearly shows that we have only phi component of electric field, and not only that, at center electric field component is 0. So, the bottom figure, it shows the electric field strength variation along radius starting from center. So, you can see that at center it is 0, then it is increasing, having a maximum inside the dielectric, and r equal to a, it represents air dielectric boundary. So, above a, that means in air it decays exponentially, and we do not have any Ez component or Er component of electric field. You can compare this electric field variation with the TE01 mode in a circular waveguide. This is also a axisymmetry mode in circular waveguide. So, almost similar field variation, but only difference is that in circular waveguide all this electric field is confined within the structure, but for the dielectric resonator in air it decays exponentially. So, we have some fringing fields, and the amount of fringing fields, it depends on the dielectric constant of this material. And now, if I want to use this resonator as an antenna, in that case we will have radiation due to the fringing field, and we will expect that the electric field and magnetic field, they should be in same phase, otherwise we will not have any radiation. And for filter application, the whatever electric field or magnetic field we have in air, they should be in phase quadrature, so that almost there is negligible radiation. And now, look at the magnetic field variation. So, magnetic fields, they form loops, and we have both the radial component and the z component. So, on the central plane of this dielectric resonator, magnetic field is maximum. There are many closed form expressions available in literature. So, this is one of them. It is accurate within plus minus 5%, you can say. If the resonator dimension is given, that means the resonator height d, its diameter twice a dielectric material epsilon r, then we can calculate its resonance wave number k naught. So, we have two closed form expression for two different cases, two different aspect ratios. When d by 2a, it is within 0.5 to 1, you can use this first formula to calculate the resonance frequency. So, you recall that k naught, this is equal to 2 pi by lambda naught. So, from that you can calculate then what is f naught. And the second one, when d by 2a is within 0.2 to 0.5. Now, the quality factor, this is one of the important parameters we frequently use to represent loss. Q in general, this is equal to omega naught into W by PL, where omega naught represents the resonant frequency, W is the maximum stored energy inside the resonator, and PL is the total power loss. So, if loss is minimum, in that case quality factor will be much higher. Now, what are the sources of losses? For any structure, passive struct component, the losses, it can be due to conductor loss, it can be due to dielectric loss, or it can be because of radiation. So, then we can define three quality factors which will represent these three different losses, and then the overall quality factor Q, they are related to these quality factors like this expression, as can be given 1 by Q equal to 1 by QC plus 1 by QD plus 1 by QR. So, where QC it represents conductor quality factor, QD this is dielectric quality factor, and QR this is radiation quality factor. So, if we want higher radiation, QR should be small. If we want to use dielectric resonator in filter application, this overall quality factor should be as high as possible, so that we can we can say that the loss inside the structure is minimum, and it stores almost all of the given energy inside the structure. Now, whatever resonator we are considering here, we did not consider any conductor. So, QC that means it is infinite, we do not have any conductor loss equal to 0, and QD it depends on loss tangent of the material, this is equal to 1 by tan delta. So, it is a property of the material, and now choosing a dielectric material which has very low dielectric loss, it can be made very high, and QR it is approximately twice omega naught into We by PR. So, it is lowest among these three. So, mainly the loss term we will be facing is due to radiation. We have a closed form expression to calculate QR, it is given here. So, it is a function of d, height of the resonator, epsilon r, dielectric constant whatever being used inside the material, and also the diameter twice a. So, let me show you one graph how the resonance frequency it varies with aspect ratio d by 2a and the dielectric constant. So, in this particular graph we are expecting three different values of epsilon r, 20, 40 and 80. X axis it represents the aspect ratio d by twice a. So, and y axis it represents normalized resonant wave number. So, k naught is twice pi by lambda naught, and epsilon r this is the dielectric constant of the material. So, it becomes as a whole it becomes a frequency parameter. We can see then if we increase the aspect ratio d by 2a, then this resonance resonant wave number it decreases, or in other words you can say resonance frequency of the dielectric resonator it decreases. So, k naught and omega naught it vary inversely with root epsilon r. It also depends on epsilon r. If we increase epsilon r, then for a given dimension obviously resonance frequency will increase, but change in resonance frequency due to epsilon r it is very small. Now, since QR is minimum among the three different quality factors, so let us see QR depends on which parameters. Again we are considering three different aspect ratios, d by twice a equal to 0.3 for this blue line, d by twice a equal to 0.5 for this black one, and 1 this is for this red one. We are plotting k naught a, that normalized wave number, versus epsilon r. So, epsilon r we are considering 20 to 90, and you see when we increase epsilon r, then this normalized wave number it decreases, and also it varies with d by twice a, what we expected from the previous graph. And the interesting thing is that QR which is shown on right side, it also increases with increasing epsilon r. Approximately QR is proportional to epsilon r to the power 3 by 2. So, if we increase epsilon r, then QR will increase. In other words, there will be less radiation and radiation bandwidth will decrease. And if we have now three curves for three different aspect ratios. So, we see that smaller aspect ratio, this 0.31, it provides lower QR, that means higher bandwidth. So, if I want to design one antenna using cylindrical dielectric resonator, we have to use then lower epsilon r and lower aspect ratio. Some properties of dielectric resonators in general: HEM11 delta mode, this is the lowest order hybrid mode. Higher order mode next to TE01 delta is HE11 delta. Now, single mode operation bandwidth is maximum for d by twice a equal to 0.4. So, actually it can be shown that the monomode bandwidth, it depends on aspect ratio, and when we use any guiding structure or even a resonator, we expect that it should be excited only in single mode, and then the bandwidth is limited by the cutoff frequency of next higher order mode. So, we have to increase the cutoff separation of these two cutoff frequencies to increase the effective monomode bandwidth of any given resonator or of any guiding structure. And it can be shown that approximately for TE01 delta mode, it is maximum when d by twice a equal to 0.4. It can be further increased by using a ring resonator. So, what is ring resonator? If we simply drill one air via inside this dielectric resonator, we call it a ring resonator. Now, how it increases the monomode bandwidth? Let us concentrate on the electric field plot. So, the next higher order mode, HEM11 delta mode, the electric field plots for this mode is shown here. You can see electric field, it is having maximum on center on axis of this cylinder. So, if I drill one air via, it is going to affect this HEM11 delta mode most. You compare this with the electric field configuration of TE01 delta mode. Let us go back to the previous slides. So, for TE01 delta mode, we have electric field minima. So, if we drill one air via inside, it will not affect this TE01 delta mode as much, or in other words we can say the cutoff frequency, it is less affected by air via placed at the center of this dielectric resonator, but cutoff frequency for the next higher order mode, which is HEM11 delta mode, it will increase if I place one air via on along the axis of this dielectric resonator. So, that is how monomode bandwidth of the resonator can be increased. Now, if I choose aspect ratio d by 2 equal to 0.4, then according to resonance frequencies, the fundamental mode is TE01 delta mode, the next higher order mode will be HE11 delta mode, then EH11 delta mode will appear, then TM01 delta mode. Now, this field pattern for this TM01 delta mode, it is very similar to TE01 delta mode. So, only thing is that we have to replace electric field by magnetic field lines, simply we have to interchange them, otherwise it looks very similar. TM01 delta mode, it has been used to design dual mode filter and dielectric cavity antennas. So, we have many applications. In filter we can use resonators, in oscillator design for the tank circuit we can use dielectric resonator, dielectric resonators also used for antennas and frequency selective limiters. So, since it is also popular in antenna design, let me discuss some basic properties when we use it as an antenna. Again, when we use as an antenna, different shapes are popular. It can be rectangular shape, it can be hemispherical, it can be cylindrical also. But if I compare the QR or compare the bandwidth in impedance matching bandwidth of the antenna, it is observed that the bandwidth is maximum for rectangular dielectric resonator. So, here in this picture I am showing one rectangular dielectric resonator, and the fundamental mode is TE111, and it is the most used mode for DRA, rectangular DRA. And so, it actually shows half of a full resonator. It is placed on a ground plane. You can see it is being fed by one SMA connectors, and the inner conductor of SMA connectors, it is drilled inside this DRA, and you can see also one slot etched in the ground plane. This is to couple power from SMA cable to DRA. Now, if I consider a full resonator, so ground plane is placed in middle. So, for this full resonator, look at the electric field plot. It looks like one loop. Z is the top direction, and this DRA, it is placed in XY plane. So, magnetic field, it is perpendicular and it forms loop in XY plane. You can look at the field plots. In XY plane, the electric field, it is perpendicular, and magnetic fields, they are parallel. So, again if I go back to this XZ plane, so on this mid line shown by x axis and blue line here, electric field, this is exactly perpendicular, or you can say we can place one PEC here or you can simply cut this resonator and use half of this resonator backed by a metal or ground plane. So, if I place a ground plane here at the mid plane, then we are having this DRA, dielectric resonator antenna, shown at the left side. Now, it radiates mainly the x component due to the x component of electric field. So, electric field in space, it will be parallel to x mostly in z direction, and this is the radiation pattern, E plane radiation pattern and H plane radiation pattern. So, E plane, this is the XZ plane, and we have highest gain in both side, both in XZ plane or E plane and YZ plane or H plane. So, you can see how this DRA is being excited by using SMA. I will show you another example. Here DRA is being excited by using a microstrip line. The inner conductor of this SMA is connected to strip of the microstrip line, and here we have a printed circuit board, one substrate. So, the microstrip is placed at bottommost layer, and top layer is the ground plane of the substrate, and slot is etched in the ground plane. You can see it looks like one plus sign, and then DRA, it is placed on it. So, that is how we can excite DRA by using microstrip line. This right figure, it shows uses of DRA in filter application. This is a rectangular waveguide cavity filter, and inside one cavity. So, here you can see we have actually 8 cavities, and coupling between 2 cavities controlled by irises. It is a cutaway view, and this dielectric resonator, basically it is a ring resonator where we have air via at the center of this resonator. It is placed inside the cavity. Because of this dielectric resonator, the overall dimension of the filter, it decreases. At the same time, quality factor increases, or in other words you can say loss, passband loss, it decreases. So, this is the use of dielectric resonators, cylindrical dielectric resonators in filter applications. So, we will take a break. After that, we will start filter. Thank you.